Hi, in this video I'm going to talk about the element distinctness problem lower bound. In particular, in this presentation first I'm going to discuss what is the element distinctness problem. Then I will discuss what is the lower bound for the sorting problem and why it can be applied directly to this problem. And later I will discuss what is the proof of the lower bound of the element distinctness problem. In particular, it is an extension of the proof of the lower bound for the sorting problem. So what is the element distinctness problem? Suppose we have an array A of n elements, and there exist two elements A and J such that they are equal, then we say that array A is not distinct. However, if for any two elements A and J they are not equal, then we say that array A is distinct. So in this presentation, we are going to discuss and prove that the lower bound of this problem is n log n. So what is the lower bound of sorting? Suppose we have an array A of n elements, and we want to sort this array. What is the number of permutation that would give us a sorted array if we don't know what are the values of A1 to an? So that would give us n factorial. And if we want to draw the decision tree of such a problem, then we compare usually to any two elements, I and j. And depending on the comparison between those two elements, if I, for example, is this, then j, then we will go to a certain path in this tree, and after comparison of all the elements inside the array, we will reach to a certain solution which represent a leaf in this decision tree. So if we gather all possible scenarios, we will have n factorial leaves. And if we want to see what is the time complexity or the lower bound of time complexity of such a problem, we have to see the worst case scenario, which represents the height of the tree, which in this case is log to n factorial. So this would yield a lower bound of n log n for the sorting problem. And now for the element distinctness problem, we have two possible answers, yes or no. So if we want to apply the same concept to this problem, the height would be in constant time. However, this is not true because in fact the number of yes leaves should be distinct to obtain n log n. However, if they are the same, then that would be true for constant time. So our main objective now is to prove that all leaves that have yes, so all the paths that have yes leaves are distinct. If we can prove this, then we can prove that the time complexity lower bound for the element distinctness problem is n log n. So now I'm going to prove that the yes leaves are distinct. To do that, let's take one array A that has n distinct elements, and an array B, which is a permutation of A. So we must prove that A and B reach distinct yes leaves. So since we suppose that A is consisting of distinct values, then A reaches a yes leaf, and same for B. And to prove that the two leaves are distinct, we will do that by contradiction. So we will assume that both A and B have the same leaf. According to the convex property of decision trees, if two points belong to the same region R, then the straight line passing through these 2 points passes entirely through R, as can be seen by this figure, where we have a convex surface. The point A and B belong to the same region R. Then the straight line passing through them passes entirely through R. And we can find 2 points I and J such that AI is less than AJ while BI is greater than BJ. To show this, we take an example of A as 2, 4, 5 and B as 4, 2, 5. So for I equal to 1 and J equals to 2, we have A1 is less than A2 while B1 is greater than B2. To see the effect of this, we will take a function f equals to wi minus wj. So from these inequalities above, we can see that f of a is negative and f of b is positive. If we take z such that z is a linear combination of xi and yi with I and j defined as above, then according to the mean value theorem, f of z will be 0. Then zi is equals to zj. Then in this case, z doesn't have distinct elements, and then it has a null leaf, which means that z belongs to a different region, which contradicts what we have seen before. So our initial assumption that a and b reach the same leaf is wrong, which means we proved that a and b have distinct yes leaves by contradiction, which means that the decision tree has a height greater than or equal to n log n. So to summarize, in this presentation, we saw that the lower bound for the sorting problem can be applied to the element distinctness problem, and we discussed why. Then we proved that a decision tree representing the element distinctness problem have distinct yes leaves, which means that the height of this tree becomes similar to the height of the sorting problem, which is n log n. Thank you.